Good day, everyone. I'm Hannah Jane Lopez, and on behalf of our group, I'm excited to welcome you to our video presentation. Today, we'll be dividing into an important topic in linear algebra, the determinants. Determinants play a key role in linear algebra, especially when working with matrices. They help us understand things like solving systems of equations, finding the area or volume defined by vectors, and determining if a matrix is invertible. So stay with us as we explore the concept of determinants, what they are, how to compute them, and why they matter. So let's start.
Determinant. A determinant is a scalar value associated as square matrix. Information about matrix properties, such as its invertibility and the volume of the parallel pipe formed by its column vectors. The determinant of a square matrix A is denoted as det A or A. It is calculated using the various methods, including the Leibniz formula, the Laplace expansion, and the Gaussian elimination.
Property of determinants. First, we have reflection property. For any square matrix A, the determinant of its transpose is the same as determinant of the original matrix. So, determinant A transpose is equal to determinant A. So, we have here a 2 by 2 matrix example, which is A equals 3, 4, 2, and 5. So first, we must compute the determinant A, which is determinant A equals 3 times 5 minus 4 times 2 is equals to 15 minus 8 equals to 7. So second, we have we must transpose the matrix A. Matrix A transpose is equals to 3, 2, 4, and 5. So in this third, we must compute the determinant A transpose, which is determinant A transpose is equals to 3 times 5 minus 2 times 4 is equals to 15 minus 8 is equal to 7. So we can conclude that determinant A equals to determinant A transpose is equals to 7.
Our next property is all-zero property. So all-zero property is if all the elements of rows or columns are 0, the determinant is also a 0. So I will give you an example, which is the 2 by 2 matrix examples. So here is the example. So as you can see, the elements of our example is 0, 0, 1, and 2. So to get the determinants, we will use the formula AD minus BC. So RA is 0, RB is also 0, RC is 1, and RD is 2. So AD minus BC. So A is 0 times RD 2 minus RB 0 and RC is 1. So 0 times 2 minus 0 times 1. So 0 times 2 is 0 minus 0 times 1 is 0. So our determinant is 0.
Properties of determinants. Proportionality, repetition, property. It is defined as if all elements of a row or column are proportional or identical to the elements of some other row or column, then the determinants is 0. To further explain, I have here I have here a step to have the determinants. We notice that the row are the same. So the A sub 1 and A sub 2 are the same, and A sub 2 and A sub 2 are the same. And that will equate to 0. So how does that equate to 0? So in solving the determinants, we need to times the elements diagonally and subtract its diagonal. So we have a sub 1 times a sub 2 and minus a sub 1 times a sub 2. So we have the equation a sub 1 times a sub 2 minus a sub 1 times a sub 2 is equal to 0. And I have example of this. So in that example, first row is 2 and 2. So that is identical. And the second row is 4 and 4. Also identical. So we need to solve it for the determinants. Let's check. So 2 times 4 minus 2 times 4 equals, so 2 times 4 is equal to 8 and minus 2 times 4 8. So that will equate to 0. Understand? Okay, very good. Then what if the identical one is from this side, from in a column? How would you solve it? So I have here another example. So example, in this example the column are the same, so 3 and 7. Okay, then let's check if it equates to 0. So let's solve. 3 times 7 minus 3 times 7 is equal to, okay, 3 times 7 minus 3 times 7 equals 21 minus 21 is equal to 0. So it is proven that in every row or columns that are proportional, it will equate to 0. The determinants will be 0. And that's what proportional repetition property.
So today we're going to discuss another property, the switching property. So it means that the interchange of any two rows or two columns of a determinant is change its signs. So example, we have here a matrix A1, B1, C1, and A2, B2, C2, then A3, B3, C3. So this is a matrix. So two rows, nasa ito na sa property, the interchange of any two rows or columns of determinant change its sign. So example ana is this one. D1 interchange si columns or si rows. So karisa lang atong i-change si A2, B2, C2, then A1. Kay two rows or may atong i-change B1 then C1. then another A3, B3, and C3. That's the switching properties. So it means D1 is equals to negative D. That's the meaning of this property. I hope you have learned something about switching properties.
The next property is the scalar multiple property. If all the elements of a row or column of a determinant are multiplied by a non-zero constant, then the determinant gets multiplied by the same constant. For example, let us consider a 2 by 2 matrix. So we have A equals entries of 3, 2, 5, and 4. To compute a determinant, we have this formula. Determinant of A equals A times B minus B times C. So first, we will compute the determinants. So to compute the determinants, we have to multiply 3 and 4 minus 5 times 2. So 3 times 4 equals 12 and 5 times 2 equals 10. So 12 minus 10 equals 2. So the determinant of this matrix is 2. To apply the scalar multiple property, the next thing to do is to multiply row 1 by any non-zero constant. So for example, we have 3. So we will multiply row 1 by 3. So 3 times 3 equals 9 and 5 times 3 equals 15. So we have now a new set of matrix. So A prime equals 9, 15, 2, and 4. To compute the determinant of A prime, we have A prime equals 9 times 4 minus 15 times 2. So 9 times 4 equals 36 and 15 times 2 equals 30. So 36 minus 30 equals 6. So the determinant of A prime equals 6. Since we multiplied one row by 3, the determinant is also multiplied by 3. So we have determinant of A prime equals 3 times determinant of A equals 3 times 2 equals 6. Next property is the sum property. So for example, we have this matrix. A equals 2, 3, 4 plus 1, and 5 plus 2. Here, the second row is expressed as 4 plus 1 and 5 plus 2, or simply 4 and 5 plus 1 and 2. So using the sum property, to get the determinant of A, we will have the matrices 2, 3, 4, and 5 plus 2, 3, 1, and 2. And the determinants, we will calculate each determinants in each matrices. So first, we will calculate the 2, 3, 4, and 5. So to find the determinants of this matrix, we have 2 times 5 minus 3 times 4 equals 2 times 5 equals 10 and 3 times 4 equals 12. So 10 minus 12 equals negative 2. Next, we will find the determinant of this matrix, the 2, 3, 1, and 2. So the determinants of this matrix is 2 times 2 minus 3 times 1 equals 2 times 2 equals 4 and 3 times 1 equals 3. So 4 minus 3 equals 1. Thus, to find the determinants of A, we will add the calculated determinants of each matrix. So, determinant of A equals negative 2 plus 1 equals negative 1. So, the determinant of this matrix using the sum property is negative 1.
Next, we have the property of invariance.
The absolute of A sub 1, B sub 1, C sub 1, A sub 2, B sub 2, C sub 2, A sub 3, B sub 3, C sub 3 is equal to absolute of A sub 1 plus alpha B1 plus beta C1, B1 C1, A sub 2 plus alpha B sub 2 plus
beta C sub 2, B sub 2, C sub 2, A sub 3 plus alpha B sub 3 plus beta C sub 3, B3, C sub 3. That is, a determinant remains unaltered under an operation of the form C sub I is to C sub I plus alpha C sub j plus beta C sub k, where j and k is not equal to I. Or an operation of the form R sub I is to R sub I plus alpha R sub j plus beta R sub k, where j and k is not equal to I. For example, determinant A equals 1, 0, 1, 2, 4, 0, 3, 5, 6. Determinant A equals 1 for this side, 1 times the absolute value of this side, 4, 0, 5, and 6, minus 2 for this side, times the absolute value of the number side of this side, 0, 1, 5, and 6, plus 3 for this side, 3 times the absolute value of this number, 0, 1, 4, 0. So first, let's solve this absolute value of 1 multiplied by 1. Absolute value of 4, 0, 5, 6 equals, the first thing we have to do is to cross multiply. 4 times 6 minus 5 times 0 equals, cross multiply this one, equals to 24. Next, we have this absolute value of 0, 1, 5, and 6 equals, same process, cross multiply. 0 times 6 minus 1 times 5 equals negative 5. Next, we have this absolute value 0, 1, 4, and 0 equals, same process, cross multiply. 0 times 0 minus 4 times 1 equals negative 4. So determinant A equals 1 times this one, 24, minus 2 times this one, negative 5, plus 3 times negative 4 for this one, equals, the answer is positive 22. Next, we have the factor property. If a determinant delta becomes 0 when we put x equals to theta, then x minus theta is a factor of delta.
Triangle property. So as you can see, triangle property is if all elements of a determinant above or below the main diagonal consist of zeros, then the determinant is equal to the product of diagonal elements. So as you can see, we have here two brackets and both of them have the same determinants. We have A sub 1, B sub 2, and C sub 3. Both of this matrix is a 3 by 3 matrix. We will talk about the first one. If all of the elements below this, the A sub 1, B sub 2, and C sub 3 is 0 or are 0, so this is what? So this is the upper triangular matrix. And now the second one is if all the elements above this, the diagonal elements, is 0, so this is the lower triangular matrix. Okay? Are we clear? Okay, so next we have here the determinant of cofactor matrix. So this is the matrix A, consists of A sub 11, A sub 12, A sub 13, and so forth, till the A sub 33. Then, our matrix C, the cofactor of matrix A. So we will have here the C sub 11, C sub 12, C sub 13 till the C sub 33. Okay, so this equals to matrix A squared, where C sub ig denotes the cofactor of the element A sub ig in matrix A. Those who don't familiar with this, Cig, so the I represents the row, then the G represents the column. So this is the formula to get its determinant. So determinant of the cofactor matrix. So I'll just attach the process of getting the cofactor of a matrix. I hope you learn and enjoy our lesson today. This is Hannah Jane Lopez. Thank you for watching.